noticed that naphthalene balls that we used to keep in our cupboards disappear after a while? Do you know what happens to these moth repellents? These naphthalene balls get converted to the gaseous state. That is, there is a conversion of solid directly into the gaseous state. Or you may call this process sublimation. This video deals with determining the enthalpy changes during such phase transformations. Let us start our discussion with a general reaction in which reactants give products. The enthalpy change accompanying this reaction is called reaction enthalpy. The enthalpy of a reaction can be obtained as the difference between enthalpy of products and that of reactants. In fact, it would be more appropriate to represent this as summation of enthalpy of products minus that of reactants, including the stoichiometric coefficients of the products and reactants, that is A and B respectively, in the balanced chemical equation. We may understand this with an example. Consider the combustion of 1 mole of methane with 2 moles of oxygen to give 1 mole of carbon dioxide and 2 moles of water. The enthalpy change for this reaction can be written as enthalpy of reaction equals molar enthalpy of carbon dioxide plus 2 into molar enthalpy of water minus molar enthalpy of methane plus 2 into molar enthalpy of oxygen. However, the enthalpy change of the reaction depends on the conditions under which it is carried out. Hence, it is difficult to compare the enthalpies of different reactions. To overcome this, the values of enthalpies are specified at standard conditions. The enthalpy change for a reaction is the enthalpy change accompanying when all the reactants and products are in their standard states. And this standard state of a substance at a specified temperature is its pure form at 1 bar pressure. For example, the standard state of liquid ethanol at 298 Kelvin is pure liquid ethanol at 1 bar pressure. Now I have a question for you. Here I have tabulated the energy required to vaporize 1 mole of water and 1 mole of acetone. Can you tell me why there is a drastic difference between these energies? Well, the answer is the difference in the intermolecular forces between them. The intermolecular forces between each state of matter are different. Hence, the energy required to transform one phase to another will be different. In fact, the magnitude of the enthalpy change depends on the strength of these intermolecular interactions undergoing the phase change. Let us discuss the enthalpy change during different phase transformations in detail. In general, enthalpy changes accompanying these phase changes may be classified into 3: the enthalpy of fusion, enthalpy of vaporization, and enthalpy of sublimation. Let's see each of these in detail. Consider melting of 1 mole of ice. Usually, melting occurs at a constant pressure, that is at atmospheric pressure. Also, during this phase change, temperature is a constant, that is 273 Kelvin. Here, when the solid form of water fuses into its liquid water in its standard conditions, the enthalpy of fusion is called standard enthalpy of fusion. That is, the enthalpy change accompanying the melting of 1 mole of a solid substance in its standard state is called the standard enthalpy of fusion or molar enthalpy of fusion. This process of melting a solid is endothermic in nature. Hence, enthalpies of fusion will be always positive. Here you can see the standard enthalpy of fusion of solid ice to liquid water, which is plus 6 kilojoules per mole. Then what about freezing? Freezing is a reverse of fusion. Thus, enthalpy of freezing or enthalpy of solidification will be same as enthalpy of fusion with an opposite sign. Next, let us discuss the enthalpy of vaporization. The enthalpy change accompanying vaporization of 1 mole of a liquid at constant temperature and under standard pressure of 1 bar is called standard enthalpy of vaporization or molar enthalpy of vaporization. For example, the amount of heat required to convert 1 mole of liquid water into its vapor at 373 Kelvin is plus 40.79 kilojoules per mole. Note, condensation is the opposite of evaporation. Hence, molar enthalpy of condensation of gaseous water vapor will be minus 40.79 kilojoules per mole. Next, let us understand the standard enthalpy of sublimation. Sublimation is a direct conversion of solid into its gaseous form. The standard enthalpy of sublimation or molar enthalpy of sublimation is an enthalpy change when 1 mole of a solid substance sublimes at a constant temperature and under standard pressure of 1 bar. For example, the molar enthalpy of sublimation of iodine at 273 Kelvin is plus 62.4 kilojoules per mole. Next, we may understand the term standard enthalpy of formation. The enthalpy change for the formation of 1 mole of a compound from its elements in the most stable or reference state is called standard molar enthalpy of formation. Here the reference state of an element is a most stable state at 25 degrees Celsius and 1 bar pressure. For instance, when carbon and oxygen in the elemental state react to form 1 mole of carbon dioxide, 393.5 kilojoules of heat is produced. Hence, the standard enthalpy of formation of gaseous carbon dioxide is minus 393.5 kilojoules per mole. It is important to understand that standard molar enthalpy of formation is a special case of standard enthalpy of reaction where 1 mole of compound is formed from its constituent elements. See here, for this reaction, the enthalpy change is minus 571.66 kilojoules per mole. It represents the enthalpy of reaction. Here, 2 moles of water are formed. The standard enthalpy of formation in this case would be minus 285.8 kilojoules per mole. That is molar standard enthalpy of formation of 1 mole of water. In fact, we can make use of standard enthalpy of formation to calculate the enthalpy change for the reaction. That is, enthalpy of a reaction is the difference between the enthalpy of formation of products and reactants. Note, by convention, standard enthalpy of formation of all elements is 0. Now let us learn about thermochemical equations and their representations. A balanced chemical equation together with the value of its enthalpy of the reaction in kilojoules per mole is called a thermochemical equation. While writing a chemical equation, you have to specify the physical state or allotropic form of the substance. The coefficients here refer to the number of moles and not the number of molecules involved in the reaction. Next, let us learn Hess's law. We may understand this with an example. Consider the formation of sulfur trioxide by the burning of sulfur in its elemental state. During the process, the heat evolved is minus 395.4 kilojoules per mole. Now, if you break down the reaction to 2 steps, in the first step, sulfur dioxide is formed, and in the second step, sulfur dioxide reacts with oxygen to form sulfur trioxide. See here, I have mentioned the heat evolved for each step. Now, if you add heat evolved for each step, you will get minus 395.4 kilojoules per mole. Note that the heat evolved through the 2 steps is the same as that in one step. This means for a reaction taking place in several steps, its standard reaction enthalpy is the sum of the standard enthalpy of the intermediate reactions into which the overall reaction may be divided at the same temperature. And this forms the statement for the Hess's law. I hope you are clear with the concept of enthalpy of a reaction. However, it will be convenient to give names to enthalpies by specifying the types of reactions. We will learn about these in our next video. Now, let's summarize what we have learned.
Manorama Horizon. Learning made simple.